Okay, gang, maybe we should get underway. So, good news is we have Damek today. He's an assistant professor in OR. He's also got an NSF math postdoc fellowship, which is complicating our teaching plans because it means he doesn't have to teach all the time. So we're trying to figure that one out. He's an expert in convex optimization, but also non-convex stuff, which is something that we're going to hear about today. Yeah.
Thanks, Shane. Thanks everyone for coming and inviting me. This is a talk that I've given a sort of more technical version in the SCAN seminar last semester, so if you're coming to this one, it'll be slightly different. So this is some work that I did with my collaborator Sasha Aravkin at University of Washington. He's a really nice guy, crazy Russian guy. He sort of had this idea to start incorporating this statistical problem into the research that we were working on. And so that's what I'm going to talk about today. And the problem all starts with the easiest, well, the nicest 2D problem you can imagine, linear regression. So the point is that imagine that you have a trend of data that's sort of clear, and outside of the data you have some erroneous points, which are outliers. You can go ahead and visually inspect this and detect whether these are outliers. You can look at box plots of the coordinates if it's like a higher dimensional linear plot, regression plot, or you can do a lot of different things to try to remove outliers. But in the end, when you try to fit a linear least squares model to this line, what you'll end up seeing is that you really, really drag down. Even by if I just had one outlier here, you'd really be dragged down towards these outliers. What I'm showing in the red versus blue dots are the points that are identified as outliers under a simple model. So points which have the largest residual are considered outliers. And usually what people do is they take these outliers after they fit one linear regression model, they remove them from the data set and they refit the line. This is what happens if you do that. So you kind of get your line shifted up just a little bit. You did remove some of these bad outliers before, but actually if you go back and look, you're not identifying anything besides these points as outliers. So this doesn't work in the end. A natural second step is to try to fit a robust loss to this data set, like the Huber norm. It actually doesn't work very well. So it actually has a worse fit than a least squares data, a least squares estimator. So the points in the diamonds are the outliers. Okay, so what I'm going to talk about today is a way to alleviate this, sticking to the least squares model, let's say, by simultaneously fitting the model and also removing the outliers at the same time. Okay, so the way to do that, that I really like, that was introduced to me by Sasha, is called trimmed least squares. So the optimization problem looks a lot like least squares, except now we have some crazy non-convex kind of combinatorial constraint. So the constraint says that we look at all the residuals under the model for the current x, and we order them from 1 to n, and then we just sum up the minimum h. I'll show you a picture of what this looks like in a second, but first let me tell you a little bit about its statistical properties. So this was introduced by Rousseau in 1985 because it's like least squares in terms of convergence rate, statistical convergence rate, but it's unlike least squares in terms of this key statistical property, namely that it has a high breakdown point. A breakdown point is the minimum percentage of data that you have to inject into a model before you can arbitrarily change the fit of the model. Okay, so least squares, you can take one bad point, insert it into the model, and then arbitrarily change the estimator. For the trimmed estimator, if you're careful in choosing the h, you can have a breakdown point of up to 50%. So you have the same exact statistical guarantees, but your breakdown point can be adjusted all the way up to 50%, depending on how you choose your h. Okay, so it's a really nice estimator in that sense because you can fit the model while also ignoring data that you consider wrong. Okay, so if you imagine that the residual is like log of the probability, negative log of the probability, you're throwing away the lowest probability points from the data set while you're fitting the model at the same time. Okay, so it's kind of a nice idea. Unfortunately, the problem is non-smooth, non-convex, and it's non-smooth at combinatorially many points. So whenever you have a tie between any of the residuals or any of these least squares terms, even in this simple 1D example, you end up with a non-smooth point that sort of points upwards and is really sharp. And actually optimizing it and finding the optimal estimator is NP hard, and that was shown by Mount at Maryland a few years back. There is a nice combinatorial algorithm for it. It takes like n to the d, where d is a dimension, n is the number of points. So it doesn't scale well into higher dimensions. But beyond the simple least squares problem, we can also consider a more complex model. Here I'm just going to consider, say, minimize a smooth loss with the same order statistic constraint. So we take the current x, we make sure that all of the residuals are ordered from 1 to n in terms of their size, and then we sum up the minimal h. That's the problem we're going to tackle today. Yeah?
Could you say something about why this choice of notation, F1, comma N?
I think I saw it in Rusino's paper. Yeah, it's just a notation for an order statistic. Okay. I think it was common at the time. Yeah. Other questions? Okay, so people have used this and proved statistical properties in the trimmed generalized linear model case. So you're not really restricted to use least squares estimators. You can replace this with like a generalized linear model or anything you want really. And further statistical results were proved by Yang and Lozano, and then Alexander Rofkin and Sasha was working on this paper before, and so they had a nice algorithm for fitting some of these estimators for sparse regression problems. But the key thing here is that this is a non-smooth, non-convex problem because we have this crazy combinatorial constraint. You can also complicate this model by adding a regularizer. I'll show you what that looks like at the end, but we won't dwell on that too much today. All right. So the natural algorithm for trimming is sort of an alternating minimization approach. This approach was introduced in like the early, I guess, well, this isn't it, but in 2005, I think, and it was dubbed, I think, fast LTE. So basically what you do is you alternate between two competing things. So first you sort the objectives for the current x, and you assign them to be g, and then you minimize the sum of the minimal residuals. And you just go back and forth from sorting all the objectives, minimizing this problem. Okay, and it's pretty nice. It converges pretty quickly to something, and it's probably the most common approach for fitting these models. It's been generalized, it was introduced for least squares, but it's been generalized to any sort of loss. But there's a couple problems with this that motivated Sasha and I to look further and try to develop better algorithms for fitting trim models. The first is that it's a little too greedy. So in practice, when you try to fit an alternating minimization, when you try to fit a non-smooth, non-convex problem with alternating minimization, your solutions converge to bad stationary points pretty quickly. And that, by bad, I mean high objective value. They're stationary, but they're just going to be very high. The second drawback is that solving this alternating minimization step here is very, very expensive, if not impossible, if the GIs are non-convex, right? Because this is already, we're assuming that we're in the high number of samples case. Let's say n is a million or something like that. H is somewhere, it's some constant proportion of n. It's like 10% of n, or 50% of n, or 90% of n. So this ends up being something like 900,000 points or something like that. So basically, you need to sort the objective and then solve a large problem. So it can be too expensive or too costly, or impossible in general. So what we did to deal with these problems was basically we dealt with them in two steps. In terms of one, we decided to, instead of use an alternating minimization algorithm, we decided to use a gradient-based algorithm, which I'll describe today. And part of our motivation for that was that gradient descent has been proved to, in certain cases, converge to local minimizers rather than stationary points that are saddled on. So it's not a completely general result, but it's good indication that this is a better idea. And the way we dealt with two is, instead of solving this giant least squares problem or giant logistic regression problem or whatever your model is, we decided to use a stochastic gradient method. And this method is one that deals with one or a few samples at a time rather than going through the whole data set and trying to compute a full gradient or trying to do a full minimization step. So these are the two parts that we did to alleviate these problems. All right, so before I tell you what the algorithm is, I first want to reformulate it in a way that looks a little more smooth. Okay, so what I do is I weight each objective term by some number w, and then I constrain the w's to sum up to h. All right, so this is a set, this delta h is a set that I'll call the cap simplex. It's closed, it's convex. Can anybody tell me what happens if you fix x and minimize over w? Sorry? Yeah, exactly. Yeah, I mean,
It's just the minimum.
yeah, exactly. So you find exactly the equivalent between the two things. And the points that have a zero weight are considered the outliers in the model. The points that have a non-zero weight are considered the inliers. You might have non-integer points, but you can always choose them so that they are integer points to get the minimum points. So we always just work with integer points in that case. All right, so what does this look like? So I got this email from here that said that we should do some stuff with blackboards in general, and then I heard that this is a terrible whiteboard from the grad students, so hopefully this will work well. So I'm going to draw the cap simplex just so we can get some intuition. It's a little bit different from the normal simplex. So let's look in the case where, I guess D is our dimension, no, n is the size of the vector, n is equal to 3, h is equal to 1, and so in 3D, in this case, what is the cap simplex? When n is equal to 3, h is equal to 1. Any ideas? It's just a simplex, right? So it's sort of easy to deal with, right? So you have this nice vector here, so this is a 1, 1, 1. It's just a simplex. It's exactly this the shaded region in this triangle, right? So then let's think about the cap simplex when n is equal to 3 and h is equal to 2. This one's a little more complicated, so I probably won't make you do it, but I'm going to do it by drawing the intersection of two things. So really the cap simplex is like the intersection of a box and a plane. So let's go ahead and draw this. So just so you get some idea of the geometry of this simplex, it's kind of an interesting set. Okay, so then what you do is you take a box here, and then here, and then you draw it out, and back up. And, well, this is bad. Getting ahead of myself here. Yeah, so then I draw this up and back here and then up. Okay. And so then what the cap simplex is this, you take these three regions, and let me color it in with a different color mark. This is getting ridiculous. So basically you take this, this part of the triangle. So you take the midpoint, you invert it, and that's the cap simplex that you're looking at. This just gives you an idea of what it should look like in 2 dimensions or 3 dimensions. And the reason I tell you that is because I want you to sort of understand what we're doing with the algorithm. So this is a talk, I guess it's supposed to be accessible to graduate students in a wide variety of fields. So I don't know if everyone knows what gradient descent is or if everyone knows what projected gradient descent is, but I'm assuming that not everybody knows what projected gradient descent is. Anybody not know what that is? So some people, yeah, okay, so some people don't know what projected gradient descent is. Okay, so this is a good point. So projected gradient descent is all about minimizing a function x over a convex set, let's say. And you can imagine the convex set looks like a ball, and then you have some the function here. So what the projected gradient descent method does is it's just like gradient descent. You take a step from your current point, say here, in the negative gradient direction, then you just project back to the ball. So you take a step in the negative gradient direction, and then project back to the ball. All right, so this is a projected gradient method. And so if you imagine that your function, let's say, is in 2D, and it's just the one that takes the inner product with, let's see which example I use here, 1, 0, x. So if you imagine that this is your function, well, and you're minimizing this over the ball, then your minimizer is going to be the one that points in this direction. And I'll draw this little vector here, and let's look at what the projected gradient algorithm actually does in this case. Okay, so step 1, it goes in the direction of the negative gradient, then it projects. Negative gradient, project, negative gradient, project. And I give you this because it basically converges in 4 steps to what the solution is going to be. And this is how it works in general. All right. So projection is kind of an easy thing, and this is why I draw the simplex here, because so if you're projecting onto it, you need to think about like how that works. a little bit in terms of the geometry of the set. It's going to look a little different than the sphere, but same principle. And now I'm trying to find more. Okay, so there's another algorithm too that I want to talk to you a little bit about. So this algorithm is called the projected stochastic gradient method. Is there anybody that doesn't know what the stochastic gradient method is? Yeah, okay, good. So, okay, so the problem is very similar to the other one, except now you want to minimize, let's say, finite sum functions, just like we are doing right now. And the idea is that every time, it's just like the other algorithm, except every time at step k, you're given some xk. This is your current estimate of the solution. And what you do is you sample ik uniformly at random from 1 up to n. So you choose one function uniformly at random, and then you update. So you choose your next iterate, which is your estimate of the solution, just like you would in the projected gradient method. So you project, that's what this notation means, onto the set this one gradient. So you choose one of the gradients, you go in that direction, and then you project. Okay? The nice thing about this algorithm is that it works because, well, one of the reasons why it works is that intuitively is because if you look at the expectation of xk given the history, xk plus 1, xk, we look at xk plus 1, right? So if we expand, okay, so if I remove this, if I just look at this term here, right? Somehow I didn't have a projection of my notes. So if I just look at this term here, right, so what is the expectation of this term? Does anybody know? So I'm given x1 up to xk, and I want to take the expectation of this gradient. All right, so it's just a forward gradient step if nobody sees. It's the average of all of the gradients, I equals 1 to n of I of xk. So the key point here is that when you do the stochastic gradient method, you're basically going on average in the correct direction. All right. So this is kind of a wild method. If you drew a similar picture on the board and you had, like, let's say your two objective functions where you had a linear objective and it was like you take the inner product with 1, 0 plus the inner product with 0, 1. It's kind of a wild method because you end up going like, you go in this direction and you project back to the set, or if you go in this direction, you need to project back to the set, and then so basically you're going some random direction between here and here over and over again. It's just, it's really a nice method, but it's pretty slow on average. And the key assumption that we use here, this will be important later, is that gamma k is going to be diminished to sort of get rid of all the noise. Okay, so those are the two sort of algorithms that you'll need to know in the back of your mind. One is taking gradient step and then projecting. The other is taking a stochastic gradient step. All right. The key point about projection, well, if you want to run a projected gradient method on this problem, we end up needing to compute this projection. And the point here is that we actually have a fast projection for this problem, just through a simple root finding in MATLAB. So this is pretty cheap. All right. Let me skip this just for time. So there's a nice algorithm called PALM that works on this problem, and this algorithm is a projected gradient method. But what it does is it alternates between two steps, right? So it does a projected gradient step on W, and then it does a projected gradient step on X. So there's a little thing I didn't mention about the projected gradient method here. And in order for the projected gradient method to work, you need to assume that the gradient of f is a Lipschitz continuous function. This is like a very common assumption here. And it turns out that if you try to apply it in this case, the gradient of this function is not Lipschitz continuous because, well, if you take the gradient with respect to w, you just get f. If you take the gradient with respect to x, you get a quadratic function, w times f. So this, in general, grows too quickly to be Lipschitz continuous. So one way we get around this is alternating between two steps. One is a gradient step on w, and one is a gradient step on x. And the pros of this method is that it has really good dependence on the Lipschitz constant, requires no line search, and has a strong convergence guarantee even for non-convex f. But the con is that it has a really high per iteration cost. Because at every single iteration, you need to evaluate each one of these functions and the entire gradient. So this is two things that we want to avoid. So what we could do instead is this thing called the partially stochastic approximal gradient method, or projected gradient method. So what you do is you set up a schedule for yourself, and I'll denote it by epsilon. And what it says is that you flip a coin. If it's heads, you decide that you're going to leave W the same. If it's tails, you're going to update W with this gradient, projected gradient step. So if you recall, our function is that G function from the previous slide, and the gradient with respect to W is just a vector of functions, and so you need to project here. In terms of the X update, you always just sample a single gradient, which is what this I does, and you go in the gradient direction. Okay, so that's the partially stochastic approximal gradient method. And again, why it works is exactly because it has this the correct expectation. So any questions? Yeah.
So I have a question for the outliers. Do you make the assumption there that all the outliers are like contaminated data, or you have some control about the data generating process?
We don't analyze statistical properties in this model. Yeah, so we left that to Roseo in the 80s. He doesn't actually have a term for what the outliers are. He just proves the breakdown point is 50%, and that the convergence rate is the same. So he doesn't have a distribution that's on the outliers per se. Yeah, they're just there.
And do you have like any benchmarks where you compare these? For example, like the easy way, if you just do truncation on the data, let's say like 99% time, how does this compare to that one? So basically, you do the truncation and then you do loss of regression of the remaining data there.
Yeah, so there's been some, we've done some comparisons on that, I believe. And I don't have them in this talk actually, but it's always been worse. There it's just not, it's not clear what's going to happen. Actually, David Rupert in our department did some work on that in the 80s also. It's called, confusingly, it's called trimmed least squares instead of least trimmed squares. So it's you have to look at two different things. But yeah, we haven't done experiments. Okay, so we have the stochastic gradient method, and there's a couple pros and cons of the stochastic gradient method. Okay, the pro is that it has a low per iteration complexity because you just sample one gradient at a time, and then every once in a while you compute all the function values. The con is that actually in this case there are no convergence rate guarantees because it's a non-convex F in general for us, and we have a non-smooth sort of projection on the outside. So as of yet, there are no convergence rate guarantees for the stochastic gradient method coupled with a projection. All right, so the key impediment for convergence here is that you cannot show that the variance of the gradient ever goes to 0 as you run the algorithm. Okay, so if you're running an algorithm and you have an estimate of the gradient, you'd like it to get better and better over time. And in fact, this doesn't happen because the gradient stays, or the variance of this gradient estimate stays constant. So it's really hard to prove any convergence rates in the non-convex case. Yeah.
You've got this constant step size gamma.
Even if
that were shrinking.
Oh, I mean, okay. So the step size gamma. I see what you're saying. Yes, that makes the variance go to 0, but I think it just makes the term go to 0, right? So it just makes the term go to 0. You can never really show that those two things are converging. So it's kind of like saying you just weighted it. Yeah, it's not going to work out in the analysis yet. Okay, so this is an impediment. So there's a neat trick that I learned about from a Francis Bach talk from a while back. And it's about reducing the variance of some random variable. The idea is that if you're given a random variable, you want to reduce its variance, you couple it with some positively correlated variable. Okay? And by coupling, I mean you just subtract it from the original x and then add the expectation. Now, if you do a quick variance computation of this new random variable, which we call z, you'll see that the variance is the sum of the two variances here, minus the covariance of x and y. So if y was equal to x, this would have no variance at all, right? Because it would just be a constant number. But the more and more correlated that y is with x, the smaller and smaller this difference is, and hopefully much smaller than the variance of x. So just coupling these two sequences, or these two random variables together can really reduce the variance. And this is sort of the intuition for the next slide. So the idea that we had, and it's not exactly a new idea, this has been going on for the past 5 years, was to replace the standard gradient from the trimming method with a reduced estimator. So what we did, we took the standard stochastic gradient and we added and subtracted some random variables y that are sort of cleverly chosen. Okay? And just as a sanity check, you'll see that if you take the expectation of v while holding all the other terms fixed, you get the original gradient back. So it's an unbiased estimate, but it will have smaller variance. And in fact, as you run the algorithm longer and longer, the variance gets smaller and smaller over time and eventually goes to 0, which allows you to prove convergence of the method that we used. We also incorporate one other strategy, and this strategy is a mini-batching strategy. All it does is reduce the size of the variance by a factor of b, because we just have a bunch of independent things we're adding together. If we take a batch of size b, the variance gets smaller by a factor b. It turns out that's really important to our convergence rate analysis, this mini-batching. So what we want to do is make an algorithm that sort of balances the size of the mini-batch, which controls the per iteration complexity, with the overall number of iterations the algorithm takes to converge. Right? So before I tell you the convergence rate guarantees, let me just show you the algorithm. So this is a proposed algorithm. It looks kind of complicated, but the key steps are two and 3 to look at first. The first thing we do is we sample B elements with replacement from 1 up to n. This is B training samples. We compute this variance reduced estimator that I showed on the previous slide. You flip a coin. If epsilon is equal to 1 or you get heads in your coin, you don't update W. So you don't do any function evaluations. And then you just go in the x direction. Okay, or in the negative v direction. Otherwise, if you end up with tails, you do the projected gradient step here. So how do we choose these yi's? Well, it turns out that the sequence of yi's, or the sequence of old x's, give you a really good candidate. So if you just take the old gradients and save them, and in fact, you don't even need to save all of the gradients. You just need to save the point at which the gradients were evaluated. Then you can just periodically, with a certain probability, I guess, whenever you get tails, you update all the yi's, and then you update this sum. So it requires a full sum over the data set in this case. The nice thing about this algorithm, it's the first provably convergent stochastic gradient method for this non-smooth, non-convex problem. Before there were no convergence rates at all for having a stochastic method. Without doing one key thing, there's a technical thing. Usually if you want a convergence rate for a stochastic gradient method in a non-convex case, you need to work with mini batches that are increasing all the way up to the size of the data set. And they have to increase pretty quickly. So it quickly becomes a non-stochastic gradient. All right, so what type of convergence guarantees can we give for this method? Well, in general, for non-convex problems, you can only really say something about the gradients. There's a missing gradient sign here, but you can only really say how small the gradient is after a certain number of iterations. You really can't say anything about how close you are to a solution. For non-smooth, non-convex problems, you have to deal with something else called limiting subdifferential, which is just like the convex subdifferential, if you've seen that, a certain function, f of wx. So what does it mean, though? Let me give you a picture graphically of what it means to be close to 0 in this set. So this is a book taken from the Bible, Rockefeller, which is my favorite book. This book develops all this theory, but basically if you want to think about what the limiting subdifferential is, you look at the epigraph of the function. So you look at the function and you look at everything that's above its graph, right? The graph has a bunch of normals associated to it, so like outward pointing points. And then whenever you see a corner, you sort of look at all of the directions that you can go out in. And the slope of the lines are the subdifferential. So those are the elements of the subdifferential. So here, you'll end up with a 0 in your subdifferential, conveniently at the minimum of the function. Elsewhere, you will not end up with 0, I guess, at all in this case. Here, you have subdifferentials going all the way up to slope infinity, so you have a horizontal normal. But this is what we measure in the end. So we measure how small, or how close there is a, how close slope 0 is to each of the points. Okay, so after k iterations, we have a guarantee on how small that is. All right, but what do they mean? What do stationary points mean for this problem? So suppose that the point where all the w's are not equal to 1, but they're all equal to 1 on the minimal subset. Okay, this is a typo. But suppose that you have a stationary point. So x star 1 is a stationary point if there exists an ordering of the indices 1 up to n, so that we order all the function values, and the bottom h are minimized. The sum of the bottom h are minimized exactly at x star. All right, and we can also guarantee more. If you have a local minimum, you'll have a local minimum whenever there is no tie for the last element in the inlier set. Right? And the intuition for that is just a small perturbation of x is not going to really adjust the orders. So actually, stationary points are pretty meaningful for this problem, unlike other sorts of combinatorial problems. So this is a pretty meaningful notion. All right, and I won't go too much into this, but the short story is that this algorithm smart will converge. The objectives converge almost surely. And whenever the sequence is almost surely bounded, you can find limit points on a full measure set. So even in the deterministic case, you need to make assumptions about boundedness. Otherwise, if you don't want to make the assumptions, you can just impose conditions on f and say the sublevel sets are bounded. So if f is less than a certain value, you can't go too far. So these are fairly common assumptions, but it's the first sort of guarantee in this case. Any questions? Okay, so this is really the innovation of the algorithm, besides the fact that it's the first stochastic gradient method. The innovation of the algorithm is the fact that there's an n to the 2/3 dependence over epsilon. So I didn't say this before, but typical methods that use a full gradient at every iteration have a dependence on n in terms of the number of gradient evaluations. So if you want to get a stationary point, you need to do n over epsilon gradient computations. With SMART, you only need to do n plus n to the 2/3 over epsilon gradient computations. And the key to this is choosing the mini-batching size appropriately. So what I said before, by reducing the variance with b, if you choose b equal to n to the 2/3, you get the best rate possible with this method. The nice thing is that, I like to say this, that n to the 2/3 is really small and n to the 1/3 is really large. Which doesn't make any sense. But the point is that n to the 2/3 is the size of your batch that you're sampling at every time step. So if you have a 60,000 point data set, 1,500 is n to the 2/3. So this is pretty small. This is a pretty small thing to have. But if you start thinking about how big n to the 1/3 is, right? So for 1,000,000 points, n to the 1/3, well, times 6 divided by 3, right? So don't make me do the math right now, but it's 100 times faster. Right, so this is a big gain in terms of the number of gradient evaluations that you need. And in addition, if certain error bounds hold, we also get a linear convergence rate, which similarly beats sort of full gradient method. So this is the big trade-off. So mini-batching somehow lets you win. All right, and then we have an extension to regularized model. It's not too important in terms of understanding this, but we can essentially handle any non-smooth, non-convex terms that don't grow downward too quickly. So if you don't grow downward faster than a quadratic, you can be included in the model. So this includes things like constraint sets, non-convex constraint sets, which I'll show in a minute. You can also model non-convex regularized with different sparsity penalties. All right, so let's get back to the original experiment. So here, if you fit the trimmed model, on a data set, so this data set has 33% outliers, and you choose H sort of, and you sort of overestimate what H might be. So in this case, I chose H equal to 44%. So I overestimated the number of outliers, and then I tried to fit the model in the data set. So you see the green line exactly matches the linear regression line that we had before, and the green line is the trimmed estimator. The green squares down here are exactly the outliers that the trim estimator detected. So we can increase the number of points in the outlier set. So if we have 48% outliers, the trimmed estimator still gets this least squares line, Huber and least squares with a refit. So this is exactly comes back to your point of removing all the outliers from the data set detected and then refit. So this is what you have. Actually, we do have one experiment, I guess, here. It gets much, much worse. Because all these points were identified as outliers. All right, so for 48%, as soon as we hit anything bigger than 50%, we identify the opposite trend. So if you have 50% outliers, who's to say what's the outlier, who's to say what's the inlier, right? So it's absolutely fine to fit the other trend, and it may be more meaningful because they have a smaller least squares residual in this case. So we identified all points in the original data set as an outlier. And then again, if you put 83% outliers, you see these are sort of slowly shrinking down here, but these are all identified as outliers, whereas Huber, least squares, and least squares for the refit all identify these points as outliers, whereas they're really inliers. Okay, so this is sort of a toy example. I did an example over the weekend, which I didn't have time to include, with BMI that Alex Townsend sent me, which was kind of nice. The conclusion was basically that 1%, doctors give you like a level for your BMI, which is body mass index, right? So if you have a BMI above a certain rate, that's really bad. You're unhealthy. If you have a BMI below a certain rate, that's also really bad. And so we fit a trend estimator on this data set, and we found that the top 1% and top and bottom 1% were the bad BMIs found with the trend estimator. And it's agreement with the doctor said, so it's kind of interesting. But we can talk more about that offline if you're interested. I have pictures on my laptop. All right, so we also fit a linear regression model on the MNIST data set. So what we did is we did K-class classification, multinomial logistic regression. Our data set was MNIST at 60,000 characters. This is why I know the end of the 2/3 computation so well. 60,000 handwritten digits between 0 and 9, and we trim with 99% inliers. Okay, so we assume that 99% of the data is good. All right. What I'm showing here are the worst offending points in the data set. And what I want from you is to guess the labels of these points. And I'm going to write them down.
9, 3.
What?
9, 3.
9, 3,
5,
5,
0,
0, 4,
8.
8. Okay. I think some sort of averaging process is going on here. It's like when you count those jelly beans in the jar. Seems like you're doing pretty well. You got them almost all right. You missed the 9. Okay, so last time I gave this talk, there were fewer people in the room, and therefore it was less accurate. But this is actually a 0. But you can see that just by fitting a trimmed estimator and then looking at all the worst points, you kind of get to analyze what are the most the points that fit the model the least well. Right, so this gives you something to look at and analyze in the end. Okay, so this is a boring table, which is kind of interesting. So, okay, so what happens here is we took the MNIST data set and we tried. Our first experiment was the following thing, and it didn't yield anything useful. So we took the MNIST data set and we decided to randomly flip all the labels with probability 1/9 or something like that, right? Between all the classes. So it turns out that multinomial logistic regression does not care at all about that. You can flip all the labels, 40% of them, logistic regression will still find a good fit. Okay? The problem for logistic regression comes when you systematically contaminate the labels. And so what we did is we systematically contaminated by adding 1 modulo 9 to each of the digit labels. Okay? Logistic regression cannot handle that. So what I'm showing here at the top is logistic regression's accuracy on this new data set with contaminated labels from 0 to 50%. Okay, so you see its accuracy as you go from here, it goes down to 89 from the 0% contamination, all the way down to 44, and for 40% you get 65. Comparing this with trimming, trimming sort of identifies the correct set and only very, I'll say gracefully, goes down in accuracy all the way up to the 50% level when you have no guarantees at all. If you have 50% outliers, okay, try something else. It's not going to work well. But at this point, you do poorly. We also measured how well they detected the correct outliers. So again, using this sorting after you fit, you see that logistic regression with 10% outliers detected about 10%. It got about 90% still here of the outliers, 82%, 71%. So it kind of goes down really poorly. Whereas churning immediately identifies pretty much all of it.
But this is subject to this data set, right?
This is just this data set.
Oh.
Yeah.
So it doesn't have, you can't claim any external validity based on this thing, right?
No, I'm just showing you that in this experiment, if you contaminate this way, logistic regression is much worse. Yeah. No, we didn't prove any statistical data about this. Yeah. Yeah, and we also have better false positive ratings in terms of identifying outliers. All right. So I should show you a plot of how fast the algorithm is, and I tried really hard to make each of the other algorithms work well. I'm showing you 4 plots with different contamination levels just to show you that that doesn't really affect the speed of the algorithm, how much you're trimming. And so the red line is smart, the algorithm that was proposed. The other line here, the second best line is stochastic gradient, and the third line is something you can think of like projected gradient, or just gradient descent. So I would expect gradient descent to do a lot better. I tried as hard as I could to make this work well. It doesn't work very well in this case. So for these non-convex problems, I don't know what it is, but I think the stochastic component really makes them work a lot better in this case. So what I'm measuring here, epochs, is the number of times you've run through the data set so far. So this is really like how many gradient evaluations you've done divided by the size of the data set. Okay? So one interesting thing is that stochastic gradient method performs really well at the outset and then just sort of stagnates, which you expect because of this step size rule. You have the step size going to 0, the gradients don't really influence the system after a certain period of time. But one interesting strategy that people normally employ is they run stochastic gradient for a little bit and then they switch to the variance reduction method. That would have been a good strategy. But I just wanted to show only each vanilla method. All right? So it does work really well in practice on everything we've tried it on in terms of speed. So I have a few more applications. I like this one because it's kind of, I would say it's creative but not statistically sound. That's what I think is fun. So this is a PCA example. So I wanted to fit, I wanted to find a PCA model, but assuming that some of the columns in the matrix were bad. Okay. So the way I did that was does everyone know what PCA is? Yeah, I think everybody should know what PCA is. Okay. Anyway, so there's an equivalent definition of PCA which you might not have seen, but PCA can equivalently be written as this minimization problem over the orthogonal manifold. Okay, if you manifold look like, well, I guess partly orthogonal manifold, so you only have a few columns. So what it does is it takes A, you can imagine like it takes A and then it pushes A down to a small dimension and then it blows it back up. And then your goal is to try to fit A as best as possible while still passing it through this terrible filter. Okay, so you want to find the best orthogonal filter that allows you to blow back up into A. It turns out that this is a concave minimization problem over a non-convex set. Right? And the reason it's concave is that, well, just do the algebra in terms of this orthogonal matrix, and everything works out. It's really a completely non-convex problem. Okay, so let's make it worse. Let's try to trim it in addition. And so the problem looks like this. You have the cap simplex still, and you have the orthogonal matrix. So this is just sort of illustrating the regularizers that we had previously. So it's trimming, non-convex constraint, non-convex jet. So we decided to use a really, really small data set so we could visualize something. This is a data set you can find from the R website. It's on the R core data sets. 43 judges were ranked using 12 numerical categories. They included number of contacts with the judge, judicial integrity, demeanor, diligence, case flow, management, prompt decisions, preparation, familiarity with law, sound oral rulings, sound written rulings, physical ability, and worthy retention. Okay, and what our goal is to do is we want to rank all of the judges in terms of quality. Okay? And what we used as our oracle was Sasha's wife, who's a lawyer. And we had her rank all the judges, just to see what would happen and see if we could agree with her. And the first thing she said is those categories are junk. Like, it doesn't matter how many contacts the lawyer had with a judge, it doesn't make them any better of a lawyer, right? And it depends on the case. So certain cases have a lot of contact with the judge, other cases have no contact, really, besides maybe phone. The other thing she said is that physical ability doesn't matter at all. And she said that demeanor doesn't matter. She said some judges are assholes, but that doesn't matter how good they are. So definitely some things were bad. So we took that into account and we decided to do 4 problems. And I guess all you can really see from this data set is the spread of the data set. So what we did is, first thing we did is we did PCA on the full data set, and we embedded all the judges in 2 dimensions. Okay? So we couldn't identify a clear sort of linear trend that corresponded to ranking. So then we decided, okay, some of the judges are preventing our fit. So we decided to trim them out. We kept 80% of the judges out of the 43. I don't remember how many that is, but it's not that large of a number. So we kept 80% of the judges in the data set. And we identified Callahan, I think this says, and a few others as outliers. So what we saw was that the fit narrowed down a lot more. And what we decided to do was to test Anna the lawyer's hypothesis that categories matter. And those are really bad categories. And we decided to trim all the bad categories out of the matrix. So how do we trim the categories? Transpose the matrix, trim the other matrix. Okay. So if you transpose, Jane's looking at me. Okay.
I'm looking at integrity, I think is the last one.
Yeah, exactly. So this is good. This is a good point. Okay. So this is the other thing. So when we trim this data set, we found that integrity actually doesn't matter for a judge, and that's probably. I don't know what I could conclude from that, but in any case, we trimmed these categories from the matrix, so we removed those rows now, because we transposed it back from the matrix, and we're only considering, instead of 12 categories, 8. All right, so we want to just keep all of those. And then what we did is we went ahead and then trimmed some of the judges out, and this is the nth linear fit we got. We got something really confusing. We got something where all of the outlying judges that were preventing the fit coming from fitting before are now on this line. And the only explanation that we can think of is that some of their rankings are just kind of bizarre. Like some of their rankings were just completely preventing the fit because some judges would have some really anomalous high ranking in one of the categories, and it was preventing them. It was basically making PCA expand everything. So the interesting part is at the end, we have this nice linear trend, and it agrees more or less with what Anna had told us before. I think these are the bad judges, and these are the good. So it's really clear, nice trend. So this is just something to try with the model. But it's nice because it has non-convex constraints, objective, and then plus the trimming on top of it. And it shows that it really can work. So this takes, I know it's like 40 points, but it takes like less than a second. Right? So it's fairly quick. And the last application that I have is tomography estimation. So this is a problem in computer vision where you want to align 2 images based on correspondences. So the idea is you estimate a matrix that takes the projective coordinates of each pixel and maps it to the projective coordinates of the pixel in the other image. Okay? The way people typically solve this is by minimizing this least squares objective subject to an orthogonality, or not an orthogonality, a unit norm constraint, which prevents H from going to 0. It's a non-convex problem already. And the interesting thing is that theoretically you only need 4 points, 4 correspondences between the points in the images in order to get a valid homography. The problem is that if you have 5 points, 4 of which are good, 1 of which is bad, you don't get a good homography. You get a terrible homography. The image warps around on itself. It's not at all similar to what you would expect. So what we want to do is find the outliers and have a very, very small inlier set, ideally with about 4 elements that fit really well. Okay, and so what are the outliers? This is what computer vision, this is the input to computer vision, all computer vision problems. you're given, say, 2 images, and you've generated a bunch of correspondences between the images. Each line represents the belief that this pixel is the same as that pixel in the other image. Most of them are junk. Even in the middle, I don't know if those are necessarily good. Okay? But if you take the model and you plug all these correspondences into it, and you trim the best, you trim 90% of the data out, and you just keep 10. This is what you get, and you still get a few outliers, I would say, but you get 90% of the data out. And you'll see that these are extremely noisy things. And I always tell people that the reason I chose 10% is because I had one supervisor that did computer vision, and he told me 90% of data in computer vision is outliers, and he's exactly right. So this is really the place where outliers are awful. So in practice, what people do is they use ransack, which is basically brute force solving trimming. You pick 4 points, you fit the model, you examine a residual. If the residual is too high, you throw those points away. You propose 4 points, you examine the model. If it's too high, you throw it away. So it's a really costly thing. You generate 1,000 proposals, let's say, and then fit the model. All right, and in the end, you do get homography, which is nice. We refined it on the smaller pixels, just full disclosure. But you do get a pretty, actually I don't think we refined this one, but you do get a very nice homography in the end. What we're currently doing is solving larger scale problems where you have multiple images and you try to generate 3D models from them. In that case, data is extremely noisy. It comes in exactly the same form of like correspondences between images, and you want to build a model out of it, even given that you have so much noise. And in that case, ransack is just too complicated because you have n images and you have to compare all points in all of the images. So it's not a good idea in general. Other future work that we're working on is we're trimming matrix factorization models with Madeline, an undergraduate student, Anna, and student Peng, who's at University of Washington in Seattle. Sasha's also involved in this problem. And that's going well. We're in the implementation stage. We just implemented all our algorithms. Now we're testing them on data sets and seeing what we can find. I think this is a really interesting application because you can imagine having survey data. If you're trimming out users from survey data, you can really identify people that are really unusual in some sense and examine them. And you can also remove them if they sort of harm your fit. The purpose of this talk was just because I want people to use trimming. I want to talk to you about it. If you're working on it, if you have any noisy data, we should talk. Further future work is we're looking at financial data now with some people at University of Washington, Seattle, trying to trim there because that seems like an obvious place where a lot of noise is happening, but it's not clear how to do this in a nice way with time series. So we're working towards that. So yeah, that's basically my goal is to say, if you're interested in trimming, you should talk, and I think that's it.
Just a question of 2 applications, but for the image registration problem, is it really pixel to pixel or is it some neighborhood of pixels that you're registering?
Oh, that's going the wrong way.
It seems like that'd be really ill-posed, because it's just the RGB value that could be anything.
It's pixel coordinate to pixel coordinate.
Ah.
So
but how would you, but no, you have to find which
so how do you generate correspondences?
Yeah.
So in practice what you do is you look at a point, you look at its neighborhood, you generate a SIF feature.
Yeah.
A SIF feature is like you take a histogram of all the gradient directions and all the directions, and then it generates a 128-dimensional vector. And then brute force, you go to each image and you do a nearest neighbor search and choose the best out of like a certain number.
So then the other question was about the integrity.
Yeah.
So these are all subjective, right?
Yeah.
So subjectively determining integrity you might be completely wrong. So that's maybe why it's not. Yeah. The other like physical disability demeanor and all those other things maybe are more objectively.
That's true. Yeah. I mean, I could have trimmed too much.
Yeah.
I quite like the idea of judges having physical ability, right?
I'm not sure what that means. But
Yeah.
So if the data has, let's say, structural breaks, wouldn't this algorithm be able to detect the patterns there, or
Structural breaks in what sense?
like let's say you usually do it with a regime switching model, right? But if you decide to do this thing, would you be able to detect that indeed these guys are not outliers, but it's just a structural break?
Okay.
Data.
You mean like if it's like a TV sort of like you have a TV penalty, you say that things should jump too quickly, but every once in a while they can.
Yeah.
Depends on how you weight it. I mean, we weren't thinking about weighting it with a TD like that. Like an autoregressive model would also be another good chance for that. Yeah, I'm not sure. We haven't looked too much into time series. That's what we're doing. We're starting now with the time series sort of data, but that's a good point.
Because this is present in financial data when you have different monetary policy is being implemented. You see usually structural breaks or certain types of things.
It might be nice to identify when that's happening because it's being thrown out as a model, and then you can identify another place to start fitting a different model. I think that it's really two models.
Yeah.
So I would claim that in your examples you didn't have outliers, you had crazy outliers.
Yeah.
Any sense of how things go when you have maybe less crazy?
What does that mean?
So for example, instead of a 4,000 standard deviation event like you had in your, suppose you had a 6 standard deviation event.
So it's going to look like it's part of the model, I think. I mean, you asked me this last time.
Did I?
And my point is that there is no like clear mathematical definition of an outlier. If you give me a data set that tells me, sort of what you mean, and
yeah, but
we
I
can
think that's what I'm getting at, right? So
yeah.
Is it the case that this does well in these kind of situations, and then if you have sort of situations that we would maybe subjectively say that looks plausible, it's still doing something sensible.
I'd have to see. I mean, it also depends on what type of model you're fitting. I mean, like in the linear regression model, you're assuming your point cloud it looks like a line plus Gaussian everywhere, right? If it still looks like it follows into the Gaussian, then fine. But if it's like a few standard deviations away, then it may look to you like it's not a good example anymore because the deviations are too high, right? Because I mean, it really depends on definition of mathematical of outlier, which has never been clearly defined by anybody.
I think it's impossible to define, right?
Yeah. So I mean, the reason I show these that question's a trap because the reason I only show these really crazy things because if it's close enough to the model, it looks like it's part of the model. I mean, it's like outliers are a diagnostic. It's like a diagnostic tool rather than a theory. So, yeah.
Have you looked at like the influence function or the leverage of like the points that SMART is identifying as outliers? Versus
No, we haven't looked at that. No, in the end we didn't look at those. No, we thought about it, but I don't think we got to it in the end. But we should, yeah.
Do you think your results are sort of quite surprisingly good? Because this is a very hard problem, right? So, I mean, were you shocked when you saw these red lines sort of plunging down, or is this something?
Oh, that? Yeah, a little bit. A little bit I was.
Do you have
well,
any explanation?
It's into the 1/3 times faster. But, I mean...
I mean, it's a non-convex problem, right?
Yeah.
Yeah.
No, it's a non-convex problem, but they're sort of attacking it in the same way. All the methods are attacking it the same way. They have the same formulation of their computed gradients going in the gradient direction.
So maybe they're all converging to the same local minima.
I'm sure well, actually I'm not sure if they're getting lower or higher. It's possible. I mean, maybe PALM, which is like the gradient method, the full gradient method, maybe that's converging to something that's a lot higher, but I didn't run it forever to see. Yeah. But my intuition, my experience has always been that stochastic gradient methods get lower objective values in the end.
How sensitive are the results typically to the choice of age?
Age.
If you have no idea what the data is like, somebody throws at you data.
Yeah.
How did you age?
Cross validation.
Okay, so what?
I mean, I haven't played too much with that.
Okay.
In these examples, I was overestimating age usually. Like whatever I thought age should be, I put 10% on it, right?
Okay.
But I haven't played too much with it beyond these examples yet. Yeah, that's the question that we're getting to right now with the matrix factorization project, which I have to talk to Madeline about soon. Again, so our students are trying to figure out exactly how they should choose age and when is it meaningful, and that's something we have to identify. So I don't think there's a good example. Yeah.
So I have another, maybe this is more of a comment that gets to the difference between outliers and things that are actually part of your model. Many of the examples that you showed, the outliers were things that were, not only were they sort of random, but they were systematically random. So they would pull your model in a different direction, right? Whereas Gaussian outliers, they're sort of equally likely to be on either side of your line. So on average, they don't affect your fit too much.
Yeah.
Like the outliers that really produce the sort of where your model showed the best results were the ones where it was like very often one direction.
Yeah.
And so one possible working definition of what a bad outlier is, an extreme outlier, is one that doesn't actually tell you anything about your model, right? Whereas if you have Gaussian noise that sort of pulls you equally in both directions, maybe throwing that out isn't so good, right? If you're not throwing out everything that doesn't lie exactly on your line, you've thrown out all of your data,
Yeah.
right?
That's a pairwise definition though, right? That's sort of like pair of points definition, because you have to look at either side of the line.
Yeah, or in expectation somehow, right? There are outliers that in expectation fit your model, and there are outliers that don't. But whether the expectation operator is right depends on what the model is.
So, Madeline, can I
Yeah.
propose that the co-authors slug this out later on?
Yeah.
So we're a little bit over time, so let's thank Damek again.